So I wanted to go back and review what we talked about in last lecture because I think I left some kind of holes in the knowledge base. And I found some other resources that I thought would be interesting to help reinforce our experience with this. So one of the big points I punched up was this idea of L deflection. And then I really didn't have a lot of data to back it up. But I found a couple of resources on the web. This is just a definition of deflection. This is from a metal stud manufacturer. And then I found out in their journal, these kind of ratings for exterior systems and allowable amounts of deflection. And the reason for this is just to give us a handle on this L value. Obviously on lightweight flexible surfaces, we allow more deflection. On brittle surfaces, we allow less deflection. And we might want to, they don't really do glass framing, so I'm sure there are manufacturing specifications for that also. But this is hyperlinked, and you can go to that. We also talked about the idea of the wind. This is actually from a couple of years ago in this lecture presentation, a Category 4 storm hitting the coast. And this year, of course, we know we had 2 hurricanes coming up through the Gulf and making landfall at Category 4. We know that's a very significant event that damages a lot of property. And we looked at one of the other things I found this week was, and this is going to get into parametric and node-based programming, but there are inside of Rhino the ability to look at wind loading. And what I found very interesting about this, and there's a link to a video here. Maybe we'll just click through that a minute. And let me see if I can find that video. And we'll play that, and I'll go full screen. But this is a way of analyzing wind loads on buildings and the responsiveness of structure, which is interesting. But more to the point, here we have the idea of a positive pressure wind load, and then we see a lot of surfaces that are pulling out, which actually have negative pressures on them. And so, and as a matter of fact, in predominant wind forces, a lot of the surfaces of the building have negative pressure loads on them. So I had mentioned in the last lecture how you'd see positive and negative values. And so we want to think about our panels being held in place, not just from positive loads against them, but also negative loads. And so this is a wonderful tool that actually is available to architects to look at, and in this case, complex wind systems on structures to determine, worst place loading problems on building facades. And we'll slip back to our presentation and try to go full screen. Okay, there we go. And another statement out of the code that kind of deals with this idea of deflection. And this is, I believe, this looks like R301. I think this is out of the residential code. I don't think I have it. I do have it hyperlinked, but it's out of a allowable from a manufacturer. But this designation here, up here it is, it's from the residential building code for 1 and 2 family dwellings. So it's not a commercial specification, but it's a real good guide about this idea of allowable deflections on surfaces. And these are allowable by code. They don't mean that the client or the performance of the surface would be satisfactory to everyone, but these are the minimums required by code. And when you get to brittle finishes, obviously we need stiffer surfaces. Another important thing to note here is that we go from L's to H's as far as the L over. And that was really something I should have really discussed in the last lecture. The L is obvious length of a beam, so when we go to vertical surfaces, we're talking about H values, the height of them. And you'll see these ideas about live load deflection ratings for spans of all kinds of framing lumber based on the spacing between the joist. And then what's important to note is this idea of live load and dead load applied upon it. And to give you an idea of the significance of this idea of deflections being a performative characteristic that our clients are concerned about as far as satisfaction in the performance of the building product, we have the idea of minimum deflection allowed by code as being L over 360, and then a little better at L over 480. 3-star as they're saying, and then this idea of a 4-star, a very stiff floor system for premium building construction, where we have L over 960. And I'll elaborate a little bit on that idea of what that L value is. And remember, when we're talking about a vertical surface, it would be an H value. So the idea is let's look at a total load on a floor system. So I took, for example, a 10-foot floor, 120 inches, with 16-inch framing spacing to come up with the idea of a tributary load. So I'm taking inch values, dividing it by 144 to get it to square feet. But that idea of a 10-foot by 16-inch width piece of flooring would have 13.4 square feet in it, and we would multiply that by the loads on it, and we have 40 pounds per square foot of live load, 10 pounds per square foot of dead load. That means that that 10-foot by 16-inch wide section of floor surface has 670 pounds of load applied to it for the calculations of deflection and all kinds of other structural issues, shear and maximum moment. But then we can take that and look at these L values. And I calculate this number out of 670 pounds because I want you to also think of that in relationship to a person walking across the floor. So in that section of floor, if somebody was walking across it, creating a kind of a dynamic on the floor of the surface, they would be representing maybe 20% of the calculated applied load on this. So when we look at these deflections, we're not saying that if somebody stands on the floor, it's going to deflect a half inch. It's going to be much less because it's a small component of this idea of the full load for that rated deflection. And these deflections these are not based on actual performances. These are the criterias for whether it meets an L over 960 criteria. So for a 10-foot long span of floor with that kind of load on it, to meet L over 120, it would be allowed to deflect 1 inch. So there's very few architectural surfaces that we have at L over 120. We have maybe there may be some roof surfaces and some other surfaces that don't make human contact, ceiling systems and that. But when we get to floor systems, we're looking at L over 360, which means that at its rated span, it can only deflect 0.33 inches. And then we get to that idea of a premium floor, and we can look at these numbers going down, down, and down until we are at a floor with an L over 960 value, which has a maximum span of 1/8 of an inch. And so we could be talking about a floor that's 20 foot wide in a high-end residence that's only deflecting 1/8 of an inch to meet that L over 960 criteria. And then this kind of goes back to relate to what I left as an L value here, but it should have been an H value. We have, in this case, at 155 mile an hour wind, we have a deflection value of L over 225, which we're thinking about a worst case event, an extreme weather event where we're really just trying to hold the building together. L over 225 might be a very acceptable value. But that gives you a sensitivity how that is as relates to other kinds of building surfaces, especially floor systems. So I just wanted to review that to give you kind of maybe a better handle on where we were going with the idea of this wall surface having a deflection to it.